you know, when only a few charts are being managed, which if you're doing it by hand, you're not doing a million, okay? You're probably doing 1, 2, 3 key properties, right, at a step, or maybe for the entire operation, for that matter, right? That kind of makes sense because we can calculate the probability of a false signal relatively easily, right? This is the probability that we get that our process is in control and we get a result that's outside the limits. Well, with plus or minus 3 signal limits, that's about 3 in 1,000, about 1 in 370. So about every 370 observations, we're going to get a false signal, even if our process is perfect. Right? It's right where we want it. It's right on target. No issues. About once every 370 observations, we're going to get a signal, and we are going to be chasing our tail. Well, if you got 50,000 to 1,000,000 charts that you're running each day, even with perfect operation on all of them and perfectly accurate limits, which means that you know sigma exactly, which is rare, right, if ever, you're going to that translates to 135 to 2,700 false signals a day. That's a little scary, right? No wonder we're frustrated. No wonder we don't have the adequate resources to respond. Okay? There probably are charts out there that actually do need to be attended to, but there's probably a lot of them that are giving you noise. Okay, so swamped by signals, organizations had to find a way to reduce them, hopefully without losing the inherent value in the charts, right? So one organization that I worked for turned to the widely available literature and discovered that the advice that all control limits should be centered at the observed process average, the X bar value. Okay? That's where they should be centered. Okay? That's what the literature said. Moreover, they found some additional advice that control limits should be recalculated at some frequency to keep them current. Okay? Well, this organization was running a lot. It was one of those organizations that was running thousands of charts a day. So they needed to automate this, right? So they set up a system that regularly recalculated control limits, always centering them around the newly recalculated process average. But being the conscientious group that they were, you know, they set up this to occur routinely, once a week, using the most recent 30 results. Okay. They had good intentions, right? So here's kind of what their control charts look like. Now what I've done here is I've simulated some data where I've actually put some shifts in here of plus or minus, plus a half a standard deviation throughout here. All right, so this process is drifting up. In reality it is. Well, if I recalculate my limits, what happens to my limits? If I recalculate my center line, right, periodically, and the process is drifting up, my center line is going to drift up, my limits are going to drift up. Right? Process control scheme is walking off with the process. Maybe not such a good thing. Right? Actually, I can put in where the shifts were. There was an initial shift of about a half a standard deviation. Right? Each of these lines is about 1 standard deviation of this data. Right? There were a couple of shifts in here, shift here, so what's that? A half, 1, 1.5, 2, 2.5 standard, we've shifted 2.5 standard deviations up, not even close to getting the signal. Well, say that close here. Okay? I'll get a signal. Didn't have to, I simulated this once. I didn't have to do a lot of simulations to get this. Okay? So, this is going to clearly reduce signals, right? But it's not only going to reduce false signals, it appears you're going to miss some real signals as well. Right? Those points right there, if we had left our limits down here, centered here, and left the limits here, those would have all been above the upper control. So we would have gotten a signal right here, kind of the first time we moved to about 1.5 standard deviations above where we were originally running. Okay? Good intentions, maybe not the most desirable results. Okay? So somebody looks at a chart like this one, which is just the chart I showed a minute ago, and says, hey, you know, we had some Western Electric or similar run-based rules, right? I mean, we got a run in here, right? We got, what, a bunch of values, 1, 2, 3, 4, 5, 6, 7 in a row that are above the center line, even though it's moving, right? We got another run here, about 7 in a row. So why don't we add some of these rules that maybe will help us catch these kind of things that we're not catching with these limits? Well, it's probably not a bad idea. However, there was an article back in 1987 in Technometrics by Champ and Woodall that showed that adding run rules raises your false signal rate. Okay? If you've got all the Western run rules applied, your false signal rate's about 1 in 10. Right? It's not 1 in 370 now, it's 1 in 10. And that's really not desirable if you're running a million charts a day. Okay? It's at 100,000 false signals potentially. Not such a good thing. Well, this organization decided to add them anyway. Perhaps due to this potential for false signals, or maybe ignorance, I don't know. I don't know the whole history here. They left the limits for the rules at plus or minus 3 sigma. Run rules with limits of plus or minus 3 sigma. These run rules are things like 2 out of 3, 4 out of 5, things like that. Usually those limits are not set at 3 sigma. If I do that and I'm looking for 2 out of 3 outside the limits now, right? Then I've got this process that I've shifted up now, not one standard, not a half standard deviation, but 1 full standard deviation randomly through here. And it clearly starts to walk off, right? And I do get 1 point out, but I never get anything like 2 out of 3 outside of 3 sigma. Okay? 2 out of 3 was the rule they actually used too. So, you know, if I apply the one result outside the limits, and 2 out of 3, then it's nonsense, right? So I've only got to apply one of them, right? If I'm going to do this, then I'm not going to do this, right? However, you know, this approach makes it even more difficult to capture even larger process shifts, right? We've shifted up here. This is the actual shift. We've shifted 1 standard deviation here, and 2 in a row here. What's that? So that's 3, 4, 5 standard deviations we've shifted up, and we got no signal. Right? Okay, but it'll reduce those false signals. Okay, we'll do that. If we actually did use more reasonable limits for a 2 out of 3 rule, like plus or minus 2 sigma, right? For a 2 out of 3 rule, and we still did this, well, these are the limits at plus or minus 2. We would have actually gotten a signal right here. Right? We would have captured this 3 sigma process shift in 3 results. Okay? We've got 2 out of the first 3 after that occurred to be out. So we would have captured it. Now, there is a way to get a handle on the effectiveness or the relative effectiveness of control schemes, of different control schemes. There is a way to do it. You know, I've got a bunch of black belts in here, so they probably know this, right? The most common way to evaluate control schemes is through this thing called average run length curves, or ARL curves. Essentially, an ARL curve just looks at the average number of samples until a control signal would be expected to occur. Okay? And it's got to be a function of the assumed process condition where you're operating, right? Nature of the process. It's also a function of the control rule. Okay? Usually the way we identify them is we talk about ARL delta, where delta represents a change in the process from the desired state, right, in control state, to some out of control state. Right? And then the average run length is nothing more than 1 over the probability of the signal given the delta, whatever the delta happens to be, the change in the process, and whatever control rule you run. Okay? Of course, if you've got no change, delta effectively 0, then essentially what we've got here is the average run length at no change is 1 over the probability of a false signal. Right? So you can get a signal when there's no change as well. And of course, the average run length when there's a change is 1 over the probability that I actually can detect the change with the control scheme I've got in place. Depends on the magnitude of the change. And here's a common X-bar chart. This is an X-bar chart set up at plus or minus 3 sigma with an accurate evaluation of sigma.